My name is Wolfgang Kinzelbach, and I would like to share with you some ideas and results from a Sino-Swiss groundwater project. I'm here talking for a whole team of people, and my talk has 4 parts. First, I want to introduce the situation of overexploitation of aquifers worldwide, and in the North China Plain in particular. After that, I define what I mean by sustainable groundwater use. Then I turn to a management system for one particular county in the North China Plain. And finally, I come to some results and conclusions. NASA and the German Geo Research Center in Potsdam have been measuring the gravity field of the Earth since 2002 with a pair of satellites. They found that the mass distribution over the globe is changing in time, both seasonally and over longer times. These local mass changes are caused by the redistribution of water. The changes are expressed in centimeter of equivalent water loss or gain, and the map shows in red tones the regions where water mass decreased, and in blue regions where water mass increased between 2004 and 2020. Melting glaciers show as decrease, like here in the Arctic and Antarctic regions. But depletion of aquifers also shows as red, like here in California or in the High Plains Aquifer in United States Midwest. Then, of course, in Saudi Arabia. In Pakistan and India, it's a combination of glacier melt and groundwater overpumping. But here, in the case which you are interested in this lecture, the North China Plain, the mass decrease is clearly due to overpumping of the aquifer system. On the whole, the world pumps about 1,000 cubic kilometers per year of groundwater, and about 1/4 is not sustainable. Now here's the North China Plain defined by the boundaries like Taihang Mountains in the west, the Yanshan Mountains in the north, the Bohai Sea in the east, and the Yellow River in the south. It is an area of about 140,000 square kilometers with more than 6 million groundwater wells. You can find yourself the mass loss in this region with NASA's data analysis tool. If you put a rectangle over the North China Plain, you find a decrease of the gravity signal equivalent to 2.4 centimeters of water column per year between 2004 and 2020, which translates into a mass loss of 4 cubic kilometers of water per year. Now, on the ground, you see the decrease of storage in the observation wells all over the plain. Here is a typical one, which has been declining by 80 centimeters per year since 1980. If we use a specific yield of 3%, we can nicely superimpose the gravity curve and the Pearson method data. The distribution of overpumping in the plain is quite heterogeneous. The aquifer system is usually divided into a shallow phreatic aquifer here on the left and the deep confined aquifer on the right. While the main pumping occurs in the shallow aquifer with the cones of depression in the Piedmont area, the drawdowns of groundwater are more serious in the deep aquifer. Due to its smaller storage coefficient, a smaller amount of pumping produces a much larger drawdown. Of all abstractions, about 63% are by agricultural irrigation and 37% for households by household and industry. Now, what is the reason for overpumping? The North China Plain is China's breadbasket. It produces 21% of the national wheat output and 13% of China's maize crop in a double cropping system of winter wheat and summer maize. This intensification started in the 1980s when China's population increased fast and more people had to be fed. One has to know that rainfall in the North China Plain is concentrated in summer, the monsoon season, and is usually sufficient for the summer grain crop, which in a normal year needs at most 1 irrigation. But the winter wheat growth season is just a part of the year here with very little precipitation. So it has to be irrigated fully. While natural rain supplies about 500 millimeters per year, the combined need of wheat and maize is 800 millimeters. So 300 millimeters of irrigation are needed on average. In the dry season of the year, streams have little to no water, so the irrigation basically relies on groundwater resources. The question is, can one go on like that? There are three ways in which groundwater pumping can come to a stop. First, there is the physical limit, when the aquifer is pumped dry. The second limit is the economic limit, which means water levels are so deep that the cost of pumping water becomes excessive for irrigation. And the third is the quality limit. Usually, water is the more mineralized, the deeper we go. Once the mineralization increases to a degree which makes the water unusable, we also have to stop pumping. But long before we reach any of the three limits, there is a number of undesirable consequences of overpumping. Let's start from a high groundwater level, which gradually declines. The first phenomenon encountered is the decrease of stream flow. When the groundwater level falls below the stream bed, the stream does not receive groundwater anymore, and in the dry season, it falls completely dry. In the North China Plain today, groundwater tables are usually already deeper than the riverbeds. Wetlands suffer from falling groundwater levels. Hebei province lost 90% of its wetlands in the last 70 years. A falling groundwater table leads to die-off of phreatophytic vegetation. That is vegetation which relies on the groundwater table for its water supply. A famous example in China are the desert poplars of Xinjiang province, which experience severe degradation due to declining groundwater levels. The next thing which happens is soil subsidence. It's up to 2.5 meters in a wide area in Hebei province. Crevices and holes in the ground develop due to the settling, and 50 such features are longer than 1 kilometer. Close to the coast, a cone of depression will attract seawater and you get saltwater encroachment. Finally, the depletion of storage makes the system more sensitive to climate change. As large storage is an insurance, even for multi-year droughts. With storage depletion, this insurance is lost. Having seen all the consequences, what is the correct way of using groundwater? There are internationally recognized best practices. I summarize them in 4 items. Pumping should stay smaller than recharge to prevent systematic decline of groundwater levels. Groundwater should be used conjunctively with surface water. It should serve as a buffer which stabilizes water availability also in drought times. The groundwater table should stay between 2 red lines, which I'm going to describe in more detail in the next slide. And finally, we can increase recharge by managed aquifer recharge. Whenever we have excess surface water, we can infiltrate it into the groundwater for later use. Unfortunately, pumping water is much easier than putting it back into the underground. Now, the red lines concept. It prescribes an upper limit and a lower limit for groundwater levels. Groundwater levels should move in between the 2 red lines. So management tries to keep them there. The upper limit is important in agricultural areas. When groundwater gets too close to the surface, it causes waterlogging and phreatic evaporation, which in turn leads to soil salinization. In the North China Plain, a depth of about 5 meters is advisable to prevent phreatic evaporation. The lower level also depends on the specific needs of a region. If phreatophytes have to be protected, it should respect their maximum root depth. If stream flow has to be protected, it should not fall below the stream bed. In an agricultural setting, as the North China Plain, other criteria are important. A declining groundwater level leads to loss of well yield. That implies that the time needed for irrigation becomes longer and longer, and possibly it's not sufficient to satisfy all the plants' need in time. Also, to combat droughts, you want to leave a certain storage reserve. In the county we are going to look at, 30 meters below ground would be a reasonable lower limit. Now, returning from overpumping to sustainable use in the North China Plain means that on average, less water can be pumped. So the bad news is that all other things being equal, agricultural irrigation and therefore crop production has to decrease. The good news is that due to the buffering effect, production is rather uniform over the years, even in drought years. Note that it may be possible to correct fluxes and reach an equilibrium of fluxes in a relatively short time of a few years or a decade, but that just guarantees that things do not get worse. If we want to raise groundwater levels, it takes much longer time to undo the result of the last 50 years. Now, the global analysis of the whole of the North China Plain is too crude for planning local countermeasures. For that reason, we now analyze a single county, Guangdao County. It's located in the south of the North China Plain with an area of 456 square kilometers, an irrigated area of 300 square kilometers, and a population of 365,000 people. To get into equilibrium, groundwater abstraction in the county has to be reduced by 20 to 25%. There are three measures available. Number one, water saving irrigation, and a radical version of this would be the return to rain-fed agriculture, fallowing of the winter crop, and increased import of surface water from the south. Let's look at the aquifer system. The shallow aquifer is about 90 meters thick, then an aquitard of about 100 meter thickness separates it from the deep aquifer, which is about 200 meters thick. The shallow aquifer is highly mineralized with total dissolved solids between 1 and 5 grams per liter. It cannot be used as drinking water, and in some places it's even too saline for irrigation use. The shallow aquifer has good recharge of about 20% of precipitation and irrigation water applied, which the deep aquifer does not have. The deep aquifer has no local recharge. A sustainable use of the deep aquifer means zero pumping. Therefore, the deep aquifer water supplied to households and industries has in the last years been substituted, at least partially, by water imported through the South-North Water Transfer Scheme from the Yangtze River Basin, and more is to come. Agriculture still needs this aquifer, which has a very low mineralization. It's very good drinking water quality. But agriculture needs this aquifer in places where the shallow aquifer is too saline and irrigation water has to be diluted with deep groundwater to guarantee yield. For Guangdao, we set up an aquifer management system. It contains 3 modules: a monitoring, a decision support by modeling, and the implementation of measures or policies in the field. The chosen options, after being implemented in the field, we can see their success or failure via the monitoring module in the next year. The cycle is repeated annually. Now, the monitoring module determines groundwater levels, pumping rates, and land use. Groundwater levels are measured by automatic observation wells. Data are transmitted by wireless connection to a central server. The decline of water levels in the shallow aquifer, here shown in gray, has slowed down since 2002. But the decline of deep water piezometric heads has even increased in speed. An item which allows estimates of water use and which is conveniently monitored by satellite remote sensing is land use. Especially winter wheat is easily identified as is the only green thing early in the year. So remote sensing can also be used to check which areas of winter wheat have been fallowed from one year to the next. Now, the third monitored item is pumping from groundwater, and that's difficult. The number of irrigation wells is large. There are about 8,000 wells, and they are mostly primitive wells, as shown here. Monitoring is difficult. So in some regions of China, smart water meters operated with swipe cars have been introduced successfully. So you have a swipe card, you switch on the well, and the data are transmitted by real-time wireless transmission. But in Guangdao, these monitors or these water meters are presently infeasible because of too high cost, and above all, too high cost of maintenance. All wells in North China Plain, no matter how primitive, are powered by electricity. So we decided to use electricity consumption as a proxy for water volume pumped. And with pumping tests, we get the conversion factors. The power supply company installed new smart electricity meters on every single well with remote data transmission once a day. So we know every day the electricity use of a single well. The system is maintained by the utility through its electricity fees. And here are the typical conversion factors. 2.6 cubic meters per kilowatt hour for the shallow aquifer, half or 1.3 cubic meters per kilowatt hour for the deep aquifer, and 11 or 13 cubic meters per kilowatt hour for pumping of surface water from the main canal to the fields. The data go to the modeling module, where water balances are computed and suggestions are made on the 3 measures to contain overpumping. That is fallowing of window weed, import of surface water, and water-saving irrigation. Now, a water balance of the county for the time from 2000 to 2014, that means before the project, shows a deficit between recharge and discharge of 22 million cubic meters per year. This deficit is mainly due to pumping from the deep aquifer, which has no recharge. Groundwater use has to be reduced by about 20 to 25% to ensure sustainability. A 2-dimensional groundwater model shows the distribution of groundwater levels. Here you see a depression cone, and it corresponds to a district with a high proportion of greenhouses. These have an even higher specific water use over the year than the combination of winter wheat and summer maize, as they produce throughout the year. The third module is the implementation of policies in the field. They consist mainly of 3 measures: subsidies for fallowing of winter wheat, subsidies for water-saving equipment, and setting of quota for groundwater use, and then water fees will be collected in the case that quota are overstepped. The subsidy for not growing winter wheat is $1,120 per hectare. It is the most successful measure so far, as farmers earn very little from wheat growing. Subsidized water saving is less successful, as farmers already make great efforts to save water. It may become more important when small farms are combined to bigger farms. This is an ongoing process, as the usual family farm with less than 1 hectare does not secure a reasonable income. Young people leave the countryside to make a better living in the cities. Center pivots, as shown here in the picture, are not suited for the smallholder farms. The envisaged quota scheme is 3-tiered. It allows free water use up to the sustainable level, then a water fee of 0.1 Chinese yuan per cubic meter, and finally this fee is doubled for the excessive pumping defined by the 3rd tier. Only greenhouses will fall into this last category. Mind that the water fee is added on top of the electricity fee, which is also about 0.1 Chinese yuan per cubic meter for pumping from the shallow aquifer. I come to my conclusions. Between 2014 and 2019, the water gap has been reduced from the 22 million cubic meters per year to about 1/2. Most effective overpumping control measures are the subsidized fallowing of winter wheat and the import of surface water from the Yellow River. Electricity to pumping volume conversion has shown to be an effective and feasible method for metering of many small irrigation wells in the North China Plain. The water fees for overstepping quota have been calculated, but they are not yet implemented due to the resistance of farmers. They are also too small, really, to have an effect. Water saving potential is low. As farmers already save water by practicing deficit irrigation, it will increase as small family farms are merged to large farms which can practice precision agriculture. The final solution is a combination of fallowing and surface water import. Fallowing is limited by the National Grain Policy grain security. Surface water imports are used very inefficiently today, and their improvement is key to the solution. Now here you see shallow aquifer, we are almost in equilibrium. The task for the future is to also get the deep aquifer into equilibrium. With this, I would like to acknowledge the support to the Swiss Agency for Development and Cooperation, the Chinese Ministry of Water Resources, and the China Geological Survey in this project. I also thank all my colleagues, and I thank you, the audience, for your patience. Thank you very much.